All right, so chapter 6, part 2, we were looking at climate change. So within these types of climate change, we have three things that we look at: trends, cycles, and anomalies, right? Let me get this to work. Okay, so trends, long-term trends, and anomalies. Let's go into these in detail. But these are the things that are caused by climate forcing, like say changes in the sun's output, and can lead to climate feedbacks. So let's look at trends, long-term trends. If we go back in Earth's history 55, 60 million years ago, the average temperature was about 12 degrees warmer. Again, it doesn't sound like a whole lot, but that is a huge difference. It was so warm that there was no ice at either pole. There was no ice at the North or South Pole. And we know from fossil records that CO2 in the atmosphere was at 1,000 ppm, 1,000 parts per million. Today we're roughly at 400. And what that means is if you took any sample of air, say a cubic foot of air, for every million pieces of air, for every million molecules, 1,000 would be CO2. So we are 400. So basically carbon was almost over twice as much as today. Okay. So obviously we've changed. We're cooler and less carbon. And what we think is geological activity, the movement of continents, which we'll talk about with tectonic activity, led to the creation of the Himalayan mountains and the Tibetan plateau. This huge creation of very tall mountains and high lands sets in motion a chain of events that cools to where we are today. And so this creation of high mountains, as we'll talk about, one of the processes that happens is it actually pulls carbon out of the atmosphere. And if we look right here, this just shows you the average daily temperature, and kind of the average temperature over the past 60 million years, right? Right here at its peak, we see that it's also when the Himalayan mountains are beginning to be built. This process of building mountains and exposing all this dirt starts to pull carbon dioxide from the atmosphere, okay? And we see that the global temperature starts to drop. And in fact, right here at about 35 million years ago, we start seeing ice at the South Pole, which is still there today. And about maybe 8 million years ago, we start seeing ice in Greenland and in the North Pole. And you can see where we are today. So this shows that the long-term trend, we have actually gradually been cooling for the last, say, roughly 60 million years. Okay, if I can. Another trend we have, if you look even closer, say the last 3 million years, and don't worry about the Quaternary period, but in the last 3 million years, we've actually had this kind of up and down cycle of hot and cold temperature called ice ages. We've had basically 22 ice ages in the last 3 million years. An ice age, they call it a glacial period, when glaciers around the world expand, and we have ice ages, and then we have what they are called interglacials. Okay? And if you zoom in even further, in the last million years, right, the glacials or the ice ages have lasted about 90,000 years, followed by a warm period of about 10,000 years. And that kind of ties in nicely. The last ice age ended about maybe 10 to 11,000 years ago in the northern hemisphere. Okay? And that last 10,000 years, this interglacial period, we call this the Holocene, the temperature has actually been very stable, pretty much the same for the last 10,000 years. So we look at this right here. This is going back about 6 million years ago, and the average daily temperature right here. And you can see here's today's average temperature. But you can see it's been a little bit warmer, and then gradually getting a little bit cooler. But overall, up and down, ice age, ice age not, ice age not, ice age not, right? So that's about the last roughly so many years. What we noticed, there's actually two patterns we noticed: this 41,000 year cycle and this 100,000 year cycle. And what we notice is these actually tie in quite nicely to what's called the Melanovich cycles. Okay, so we think this explains why we've had ice ages the last so many million years. These are tiny little changes in the orbit of Earth. So the first one, orbital eccentricity. We don't orbit the sun in a perfect circle. It's actually kind of an oval. So sometimes it's more like an oval, sometimes it's more like a circle. It kind of stretches like a rubber band. And it takes 10,000 or 100,000 years to go from the short to the long. So there are some times when we are much closer and much further from the sun. Okay? And if we're closer to the sun, that means more energy, warmer periods. Another one is the orbital tilt. So remember we talked about how the Earth is tilted at 23.5 degrees, which is why half the Earth has warmer summers and the other has cooler, that kind of thing. Well, the tilt isn't perfect. It varies. It goes between basically 20 to 24 degrees. Now, if the tilt is less, if it only is tilting 20 degrees, that means we have cooler summers and we have weaker winters, a more even pattern. If the tilt increases to 25, that means we have colder winters and hotter summers. And the last one is called precession. This one's kind of tough. Basically, if you ever think about a spinning top, right? The top spins, but sometimes it actually spins like this as it spins. These three things interact to change our orbital geometry, and it varies the amount of energy we get from the sun. So these tie in quite nicely with the climatic record. These also lead to internal climate feedbacks. So if you have a colder winter because you're orbiting further from the sun, that leads to more snow on the ground. More snow on the ground leads to more reflectivity, which makes it even colder, which makes your winters even longer. Okay? So these are climate forcing factors. We also have just random events, things out of the blue that we can't predict, have no pattern. Sometimes the sun gives off more energy. It literally shines brighter or it dims and we don't know why. An example would be sunspots. Sunspots, dark spots on the sun, we don't know what causes them. We're not positive of the effects, but we do know this. The Little Ice Age had less sunspots. Maybe that was a trigger. We don't know for sure. Volcanoes. Volcanoes erupt on a different schedule. Sometimes they erupt all the time, sometimes they don't. A good example would be Mount Tambora. Mount Tambora in 1816 in the Philippines erupts with so much violence and puts so much dust and ash in the atmosphere that it cooled the global temperature for about a year. The next year, 1817, it was so cold that in Pennsylvania and Virginia, in the middle of summer, they still had ice over lakes and rivers. Right? So, these are random events. Another example, the Younger Dryas, just a random event in the northern hemisphere, roughly about 13,000 years ago, as the Earth was coming out of the last ice age, was getting warmer, and then all of a sudden, for about maybe 500 years, it went back into an ice age, out of nowhere. And we think it was because the ocean conveyor belt system shut off, and I'll talk about why. But the ocean conveyor belt, it's these series of currents that are all connected to the ocean that move heat. Now this may sound familiar. This may sound familiar. I'm sorry, it's bath time in a little bit. We're getting my son ready for bath. I'm trying to get your lecture done in time. This all may sound familiar. If you're a fan of really bad science fiction movies like I am, and you've seen this movie, The Day After Tomorrow with Dennis Quaid and Jake Gyllenhaal, he's in New York City, and the Ice Age happens overnight, and they're trapped at the New York Library, and his father has to save them. Really bad science fiction, but it actually uses this whole premise of the Younger Dryas. And what we see is here, 15,000 years ago, the Earth begins to warm. It gets warmer and warmer and warmer, and all of a sudden it just plunges for about 1,000 years, extremely cold, and then warms right back up. And here is a map of the ocean conveyor belt system. The red lines are warm ocean currents. We've talked about the Gulf Stream quite often. There are other ones. When the Gulf Stream ends, the water sinks to the bottom of the ocean, and then you have a cold ocean current. And these are all like one big rubber band. You can see they're all connected. If the rubber band snaps somewhere, the current stops. So we think something happened to snap the rubber band right here, which started the Younger Dryas. And what we think was this. The last ice age, this huge area is one big sheet of ice. It was a glacier that at its peak, it extended right down here to Ohio and Indiana and southern Illinois. As the ice age began to melt and the world got warmer, it melted and shrunk back. And as it melted, it formed these big, huge lakes, like puddles, if you will, right here. Where the Great Lakes currently are. This is currently a lake in Canada. Much bigger. but the puddles had nowhere to go. They couldn't get to the ocean because they were blocked by the ice. Okay? And we think what happened was that something happened to break the ice right here. The ice melted enough, and suddenly all this water just drained out into the ocean. Now think about it. This is ice melt, so it's cold, fresh water. Okay? And let's go back. All of a sudden, you have this huge pulse of cold, fresh water. It comes right here. It cuts across the northern Gulf Stream, which is warm, salty water. And the cold water acts to shut it off. It breaks the rubber band right here. It stops the Younger Dryas. It stops the Gulf Stream. All this warmth stops going to Europe. Europe gets colder and colder, so snow starts to fall. More snow falls. More ice forms. Increased albedo makes it even colder, and the northern hemisphere plunges back for about another 1,000 years into a mini ice age. Now, I'm going to pause it right here because you're probably asking the question, well, how do we know what climate was like if we don't have records? If nobody was taking the temperature every day, how do we know how cold it was? And we're going to talk about paleoclimatologists and how do we know how cold it was or how hot it was when we come back.